Okay, I don't have anything to return today. I'll give you a bunch of stuff back tomorrow. Um, so today we're going to get into the next topic, which is centroids. First, I was asked if I could do number 12 from rigid bodies, so I'll do that. And then we'll do centroids. And I think after, I just want to get to the new topic so you can start working on some new problems. But I'll go back and do another rigid body, 3D rigid body problem after we do centroids, maybe tomorrow or something. But let's do number 12 from rigid bodies. So the hardest thing about rigid body problems is drawing them. And then the second hardest thing is solving them. Everything else is easy. Okay, so this end of the beam is connected to a ball and socket joint at the wall at A. And then the end of the beam is connected to a cable that connects to a pulley. And that's a separate cable than the one that goes through the pulley. And the one that goes through the pulley connects to the wall at two spots. Here and here. And now the dimensions. Those two are both 5 feet above the height of A. That's 5 feet over here too. And each of those is 4 feet horizontally from the center line where A is. So there's a lot of symmetry. And then there's a force acting down from this sleeve. And the idea of this sleeve is it really doesn't change anything about the problem. You would do the problem the same way if this wasn't here, but I think the intention of that is just to show that since that sleeve is free to slide along the beam, there can't be any component of the force parallel to the path that it travels on. If you took a cable attached to this and tried to pull it this way, it would just move along, you know. So the only force you can apply to this thing is straight perpendicular to the beam. That's how it's drawn anyways, so I don't think there's any point in that really, but they're always looking for new ways to make things look confusing. And that's a force F. And now we need a few other dimensions. That distance is 5 feet. That distance is 5 feet. And the coordinate system, this horizontal distance here is 2 feet. What are the reactions? And we need to come up with these reactions in terms of that variable F. Okay, so free body diagram. It doesn't give any mass, right? Okay, so there's the object. There's a downward force of F. I didn't draw the coordinate system, but they did give us a coordinate system. It's a little different than the one I usually use. So the z-axis is up. The y-axis is along the beam's long axis, and that means that the x-axis has to be this way for it to be a right-handed coordinate system. Okay, force F acting down. This is a ball and socket joint. So you have an unknown force vector and no couples. And then here you have a tension, call that T. And we want to solve for those two tensions coming out of the pulley. So maybe we should include the pulley in this so that we can, if we, if we could solve that the way I drew it right there, we'd solve for that variable T, but that's not what we're asked for. We're asked for those, we need to know the tensions in that other cable that's going through the pulley. So I'm gonna include this and the pulley, and then the external loads are going to be tensions in both of those two directions, and it's the same cable, so we can call those both T. The pulley, we don't, except that we know that looking at it directly from the side, put it on here. Looking at it directly from the side, it would look like this, So we can imagine completing the triangle and figure out how far vertically it has to go if it goes horizontally 2 feet. You know what I mean? So we know, here's what we know. If we complete this triangle, this height is 5 feet. This distance is 10 feet. And we know that the pulley is here, where this is 2. And so this has to be 1 because those are similar triangles. Okay, so this pulley is, let's figure out the coordinates of this pulley location. So if it's the coordinates of this point at the end, well, I'll just give them the names that they have. Okay, so in the problem, this is given the name B at the end. The pulley is given C. So let's come up with the coordinates of those points. A is the origin. B is 0, 10, 0. What? C. Oh, E. Yeah, thanks. In the problem, they call this E. And they call this one D, and this one C. Okay, so the point E is at looking at this picture, it's at 9y, and then 8y and 8y and 1z. So E is equal to 0x 8 1. The point C is negative 4x 0y and 5z. And the point D is probably just positive 4, 0, 5. Yeah, 4, 0, 5. Any questions about those coordinates, getting those coordinates? For E, we know that this point here is 0, 10, 0, and we know that it's 2 back towards the origin along the y-axis and 1 up from the origin along the z-axis. Also, notice that this F is not something you can solve for. That's the applied force. We're going to get all this in terms of F, which means we have 5 total variables. So for us to be able to solve this, one of those 6 equations that we're going to get has to be 0 equals 0, yeah. Okay, so let's fill out the table. Pancake, artist, row, 4, marzipan. So first I'll do that force vector R. It's at the origin. Might as well put the about point at the origin. So the row vector is 0. The force vector is Rx, Ry, Rz, and that cross product is the 0 vector. Next is that force F. That's at the location 0, 5, 0. So the row vector is 0, 5, 0. The force vector, that's in the negative z direction, so 0, 0, negative f. And the moment is negative 5f, 0, 0. And then the last one is, well, I guess we'll do those two separately. They're both acting at the same point. They're acting at that point E. And we calculated the coordinates of that, 0, 8, 1. I'll call this this is the force from that cable that goes to D. Do that one first. That's acting at 0, 8, 1. The about point is the origin. The row vector is 0, 8, 1. And now we have to figure out that force vector. So how are we going to express the force vector applied by that cable? Yeah, we're going to find that unit vector. So so for cable 1, or the cable D, a vector in the right direction goes to the point D, 405. And its starting point is 0, 8, 1. Yep. I think that's what Z is the third. This says negative f in the z direction, and that's how they have the coordinate system defined. Yep. That's what we usually would call y. And so the vector in the right direction, in the same direction as that cable force, is 4, negative 8, 4. And so now we need a unit vector in that direction. Can someone figure out the components for that unit vector? Anyone with a TI-89 I know can just use the unit V function to calculate that. What? Okay. Okay, and then 0.408. Okay, thanks. And so then the force is just that times T. And then for cable, the cable going the other way, the one going to C, if you can see the symmetry that's happening, it looks like it's just going to switch the sign of the x component. So you can do it the same way, but you'll just get this force vector being equal to negative 0.408 t, negative 0.816 t, positive 0.408 t. Any questions about either of those? Why? What's the symmetry I'm thinking of there? Well, okay, so first of all, you don't have to notice that, and you just go through these steps again, and you'd get that answer. We'd be going, to get the vector in the correct direction, we'd be going from the point, we'd be going point C minus point E, which is negative 4, 0, 5, minus 0, 8, 1. So you get negative 4, negative 8, positive 4. The only thing that changes is the signs. And so just the sign of the x component changes. Okay, so cable D, this force vector is negative 0.408 t, negative, no, that's, I'm doing the wrong one. So cable D is positive 0.408 t, negative 0.816 t, positive 0.408 t. Can someone calculate that cross product? T. Okay.
0.408.
Okay.
And then negative 3.264.
Okay. And then I'm just finishing cable C here. So the force vector is negative 0.408 t, negative 0.816 t, 0.408 t. And can you tell me what that cross product is?
It's the same thing, but y and z change signs.
Okay. 4.08 t, negative 0.408 t, positive 3.264 t. So now Newton's second law. Says Rx, Ry, Rz plus 0, 0, negative f plus 0.408 t, negative 0.816 t, 0.408 t, plus negative 0.408 t, negative 0.816 t, 0.408 t equals zeros. I said at the start of working on this problem, one of these equations was going to have to disappear. Oh, no, it doesn't disappear yet.
It will in this rotational.
We're going to see. Okay, yeah. Right. And then the rotational equation says negative 5F00 plus 4.08T, 0.48T, negative 3.264T, plus 4.08T, negative 0.4, this should have been 408. Okay, so back to the third term. The y equation is negative 0.408T. The z term is 3.264T. And that's equal to zeros. And we actually I said we have 5 variables. We don't have 5 variables because these two t's are the same one. We have 4 variables, so 2 of these equations need to go away, and they do. The y equation says 0 equals 0, and the z equation says 0 equals 0. So we have a system of 4 equations for 4 unknowns. The first equation says Rx is equal to 0. That one's easy to solve. The second one says Ry is equal to 0. The third... those match, don't they? Yeah. That's equal to 1.632 T. The third equation says RZ minus F plus 0.816 T is equal to 0. And the fourth equation says negative 5F is equal to 8.16 T. And I got a sign wrong here. There we go. So you can calculate T in terms of F. T, what's 5 divided by 8.16? 0.0613 F. And then RZ is equal to 0.816 times this. You know what I mean? F minus 0.816 times 0.613 F. I just moved it there for some reason. Because I knew I was going to have to do substitution to express one in terms of the other one. You actually, your calculators will do this with reduced row echelon form. If you just enter the variables in there, it'll give you the answers in terms of the variables. So you didn't have to do this with substitution. For some reason, that occurred to me as the way to do it. So what do you get for this? for RZ. It should be something less than 1F, right? 0.5F. And then our Y is equal to 1.632 times 0.613F. Oh, F. So yeah, you could have also done it the same way we always do it. I said that we have 5 variables, but I wasn't noticing that 2 of those variables are the same one. So we really have 4 variables. Oh, you're talking about F. Yeah. F is like the parameter. It's saying like the question is if we apply a force F, what kind of loads are going to happen at the joints? You know, it's saying we don't know what F is yet, but how are those reactions going to vary with F?
So then how would you plug that into a calculator?
Okay, so you could plug it in like this. Right. So here's your system of equations. You have 4 equations. This is the first one, second, third, fourth. And then your variables are Rx, Ry, Rz, and T. So the first equation says Rx is equal to 0. These are all zeros. Your second equation says 1 Ry minus 1.632 times T is equal to 0. Your third one says, now we're treating F like it's a constant, not a variable. What?
In that second one, right?
In what? Oh, yeah. Yes, thank you. Yeah, so the F is just like it's a number, and it'll solve it in terms of that. So your third one will say 1 RZ plus 0.816 T is equal to F. And your fourth one says 0.816 or 8.16 T is equal to 5F. And you'd enter it in just like that, use reduced row echelon form, and it'll give you answers in terms of F. Any questions about that one? Let's see. So centroids. You want to do one more rigid body problem, and you can work on it together, and then we can. Okay, let's do that, and we'll get to centroids when we get to them.
I got a question.
Yes.
Okay, so I did number 9, but Okay, my question is, like when we have, let's say we have three forces, I mean, in the X, Y direction, and there's a couple on like two of them that say Y and
Yeah.
Z, but it's like not on X.
Yeah.
Like, how do you know which force doesn't have the couple? Like, if we could look at number
Yeah.
9,
Sure.
we can kind of understand that.
Yeah. Okay, so the free body diagram for this. The body looks something like that. That one's just a normal force. That's not too tricky. It's weightless, I think. Okay. There's a 5,000 Newton force applied there. But now the question is, what's happening at this pin joint? This pin joint is a bracket. Like if you imagine, so first imagine the translations. The point that's connected to that pin, imagine trying to move, think of nothing else connected to this body except that, that pin joint. Can you translate it this way, or this way, or this way? You can make it, okay, so this is it. Now we're not talking about the rotations, because you can make it do this. But this point that's being gripped by the pin, you can't make it translate this way. You can't make it translate this way because the bracket's holding it in place. You can't make it translate this way because of the pin. And so because of the fact that you can't translate that point in any direction, you have a full force vector acting. So I'll put that in first. So yeah, you got the full force vector acting. I'll call that R. But now what you're asking about is, how do you know what components of the couple you have? So now think about what motions are allowed by this bracketed pin. It can move freely this way, right? So we know there's no couple parallel to what I would normally call the x-axis there, because it can rotate freely about that. It can rotate freely about that axis. But now think of rotations about the other two axes. This axis, a rotation about what I would normally call the z-axis there, would be like this. And you know that the bracket prevents that. So there has to be a component of a couple this direction. I'll call that mz. And then a rotation about what I usually call the y-axis would be like this. And it doesn't allow that motion. So you know that there has to be a couple this way. Then there's also the issue of those couples are only present in the equations if they're needed for equilibrium. You could think of that as one way to think of it is try solving the problem without those couples there and see if it's possible. You know, if it is possible, then you don't want them there. If you get to the end and you can't solve it, then go back and put the couples in. But that's a pretty time-consuming way to do it.
Hey, Garrett, when I was looking at this problem, I kind of
Where the couple is?
Yeah, instead of a couple, if you had a contact force that was perpendicular to that surface, and that prevented the movement in, because it can move in one direction, it just can't move in the other, right? Or am I,
It can't translate in any direction, and you could do it that way, but it would be a way more. Yeah, that's not the way you want to do it. You want to think of that as a pin joint with thrust.
Do you know from the picture whether it's with or without thrust?
Well, in this
It looks
case,
like the pin actually goes through a little ways, and you can't tell if there's something on the other side.
you can't tell if there's something on the other side. Yeah, if you assume there's something on the other side, then you can tell from the picture. If you don't, then I guess you can't tell, and maybe I should have said that in the problem, that it provides thrust. In the Creo file, that bracket has another side. It's just hidden.
oh, okay.
Any other questions about that? Oh, so going back to, so how do you know when you put those couples in and when you don't? I think my best advice is if you're, well, I think really the only time that you don't use those optional couples is when you have two separate pin joints that are coaxial. If you think about so if any problem where the rotation is allowed by two pin joints that share the same axis. Okay, those are the problems where you skip those couples. Okay. If you have a single pin joint like this, there's nothing else, no other reaction loads that can prevent those rotations, and so you have to include those couples.
I have a question about the
Yeah.
rotation of that couple.
Mm-hmm.
So it looks like from the drawing,
Yeah.
like how do you know that it's at the same, I guess, Y as the 5,000?
Yes.
Isn't it like one of the important things that we're supposed to remember about basic? Yeah, it's important.
I just drew that dimension in the wrong place. So you're right about that. That was not my intention for that to be something that you had to worry about. That should have given the height of the pin. Yep.
But shouldn't that matter? I don't think it should matter, like the height, because you said it yourself that if we can move the force vector anywhere along the line of action
Mm-hmm.
without changing the behavior, so basically
Right, but we don't.
You can move the 5,000. You can move the 5,000 anywhere.
Yeah. That's right. The 5,000 you can move. It's that pin force that's a concern because you don't know the direction of that force, so you don't know what its line of action is. He was asking where the location where that force is that's applied by the pin. You know what I mean?
unless you just put it as a origin, the pin.
But then you have to know the relative positions of where that pin force is applied and where the other forces are applied. And what I really meant to do with that dimension was just give a dimension so you didn't have to worry about it. I just drew the dimension going all the way instead of just to the height of the pin. So like if you draw it from the side, the force applied by the by the pin is this way. And you need to be able to figure out the distances from, and there's a force applied here, and you need to figure out all of the vectors from one to the other one. And yeah, the way I have it drawn now, it looks confusing, but that wasn't my intention. So this distance is supposed to be 0.4 meters. And this distance is supposed to be 0.25 meters. Any other questions about that one? Okay, I think I introduced this one at the end of class last time, but we didn't do it. The one with like the holding up the manhole cover. Terrible. And then there's a cable that goes from the front of the manhole cover to the wall. This distance is 0.48 meters. The diameter is 0.48 meters. The horizontal distance to the support is 0.16 meters. And the height to the support is 0.24 meters. And that support is right above the bar. The mass of the manhole cover is 30 kilograms. And there is axial thrust at A, but not at B. And we want to know what's the cable tension And what are the reactions at the two pin joints? Any questions about that problem definition? Okay, let's, you can take a break whenever you want. Let's, I'll start working through this problem, let's say at 10 after. Okay, so take a break, think about this problem for a while. Is that too soon? 15 after?
20 minutes.
Yeah, is that too little, too much?
That's awesome. Yeah, no.
Okay, okay, great. 15 minutes after, I'll start going through it.